So the third lecture in Unit 3 is the last lecture of our gravitational fields. After this, we're going to move into electric fields, and then after that, magnetic fields. This is section 6.2 of your textbook. And the first thing we have to do in order to talk about orbits is to understand what a satellite is. Now, you've probably heard the term satellite, and you think of a kind of like a technological device that orbits around the Earth. But a satellite is really any body that orbits another body, that revolves around another body. We have natural satellites, like planets, moons, and stars, and we have artificial satellites. And in the case of a natural satellite, examples would be the Moon, which is a satellite of the Earth, which is a satellite of the Sun, and the Sun, which is a satellite of the Milky Way, because the Sun is orbiting around the center of the Milky Way galaxy. So artificial satellites are the ones that humans have made. There are a number of examples. The International Space Station, the series of GPS satellites, RadarSat-1 and RadarSat-2. And in your textbook on page 297, they go into a little bit more about how GPS satellites work. And I just need to correct a little bit because this textbook is a bit older. At the time when this textbook was written, there were 24 GPS satellites. There are now, I believe, 33. Also, at the time of this textbook, GPS wasn't as accurate. It gets more and more accurate the more satellites we add. And the coverage at the time of this textbook also wasn't completely global. Now the 33, I believe, satellites of the GPS system cover the entire globe. They are accurate within, I believe it's 5 meters to, I think they can go as close as 10 centimeters, I think, something like that. So they could get very accurate. And how these satellites work is that at any point in the globe, you have a minimum of 3 satellites that are covering that area. So the satellites can collect information in a kind of in a circular area of the Earth, and what they detect is the distance away from the point directly below the satellite, but they don't know the direction. So, for example, if we look at this S1 satellite in that image, it knows that there's a boat that is X distance away from the center of its coverage area. So it knows that that boat is somewhere along that circumference. When we add a second satellite, the second satellite could detect the same device, the same boat, and it would know that boat is, I guess, Y distance away from its center, and it would then know that boat is located on the circumference of its circle. Although now we have 2 satellites that are detecting 2 circular ranges of a possible location. The 2 points where those circles intersect, because 2 intersecting circles will always intersect at 2 points unless they're directly touching each other. We've now narrowed down the location of this boat to 2 spots. Now, if we add a third satellite, that third satellite, it would be able to say where the location of that boat would be along its circumference. And I don't exactly like how this image is showing it because it's not technically correct like that. The third satellite would know that the boat is, say, Z distance away. And it would then have a third intersection point. So imagine 3 circles intersecting. And based on the fact that these circles would have to intersect at another point, it would be able to determine that this triangulated point, the three spots where or rather the one spot where the three circles would intersect would have to be the point of the object. In this case, it's looking for a boat. And it would be able to detect that to within 5 meters of its actual position. So I'd like you to copy down as definitions the definition of a satellite and an artificial satellite. Now, a satellite orbits the Earth in quite often in a circle. And we're going to focus on just a circular orbit. And in our case, because the math is a bit more complicated when we start looking at elliptical orbits, although elliptical orbits are arguably they're more common, we can estimate for a lot of the work that we'll do in this course, we just assume circular orbits rather than elliptical orbits to make the math simpler. But just know that when you get into university, these calculations will be a bit more complicated. So when Newton developed the idea of universal gravitation, he also theorized that the same force that pulls objects to Earth also keeps the moon in its orbit. One difference, of course, is that the moon does not hit the surface of the Earth. The moon orbits Earth at a distance from Earth's center called the orbital radius. The moon's orbit is similar to the orbits of the planets around the sun. It's actually elliptical. And then again, it says here, we just assume it's circular. I was already explaining that previously. So how do we find out what this orbital radius is of a circular orbit? And we go back to what we learned in Unit 1. We were talking about centripetal force. The centripetal force is equal to, if you remember, it was m times our centripetal acceleration. And the force of gravity is equal to m times that acceleration, which was g, lowercase g. And we know that we learned in the previous lecture that g is equal to big G times the mass of our planet or our larger body divided by the distance between the two squared. And we know that centripetal acceleration, or rather centripetal force, can also be written as v squared over r. So if we rearrange this question for v, we end up with the orbital radius. And this shows up on your formula sheet, so you don't have to do that rearranging. But I think this shows up in Unit 2, whereas we use it more in Unit 3. And this equation is true for any orbiting body in a central gravitational field. Notice that the mass of the moon or the mass of the satellite is not needed to solve this because it gets canceled out in the second line. We have MACMG, so we divide that out. And I think I said earlier that it was centripetal force. It's actually the centripetal acceleration is v squared over r. And our G, that gravitational field effect, is big G, mass of the larger body divided by r squared. So please copy this down. Orbital speed, and copy down the equation and also the what the variables mean. So we'll do a few problems using that equation. These are rather simple. So it says here to determine the speeds of Venus and Earth as they orbit the Sun. It gives us Venus's orbital radius. It says while Earth has an orbital radius of 1.49 times 10 to the 11, and we have the mass of the Sun, which is 1.99 times 10 to the 30. And I will just take a quick break before we solve this to say that in your textbook it often will ask you to calculate things, and it will not give you the mass of the Sun or the mass of some other planets. I think somewhere in the textbook, I can't recall which page, it has a list of what these are. So assume that those are constant values that you can substitute in. That'll help you solve these problems. And for the Sun, it's 1.99 times 10 to the 30. So we're looking at the orbital radius. Our g, I'm going to save this into my my calculator's memory. So that's stored in my memory now. So that's my g. Now I have to find the square root, so I'll start by putting a bracket. I'm using my big G, and I'm solving for Venus first. So the mass of Venus is irrelevant. We need the mass of the Sun, so it's times 1.99 times 10 to the 30. And then I have to divide this by the radius on which it orbits. So dividing by that orbital radius, for Venus it's 1.08, and that's times 10 to the power of 11. I can close the bracket and find the square root. I can raise this to the power of 0.5. So I end up with 35,000, and again written as scientific notation. That's 3.51. We have 3 significant digits, times 10 to the power of 4. Doing the same calculation for Earth, I start with my G times the mass of the Sun. I don't need the mass of the Earth. Divided by the orbital radius. And then I can find the square root of this. And I end up with 2.98 times 10 to the power of 4 meters per second. Another problem here, it says that material has been observed in a circular orbit around a black hole some 5,000 light years away from Earth. Spectroscopic analysis of the material indicates that it is orbiting with a speed of 3.1 times 10 to the 7 meters per second. And the radius of the orbit is 9.8 times 10 to the 5 meters. Determine the mass of the black hole, assuming the matter being observed moves in a circular orbit around it. So here we need to rearrange that equation to find out mass of the planet, or mass of the larger object. So when we rearrange that, I'll let you try to rearrange that yourself, but I'll just say what that rearranged equation is. It would be MP equals V squared times the radius of the orbit divided by G. So MP we need to solve for, times the, that equals our V squared. So this material is, I'll put this in brackets here, 3.1 times 10 to the power of 7. That's our V. We have to square that. We have to multiply that by our radius of orbit, which is 9.8 times 10 to the power of 5. And then we have to divide that by our big G. We end up with a very large number here. And we need, we actually should list this as 2 significant digits because we only have 2 significant digits. So this should be 1.4 times 10 to the 31 kilograms. So this question here, it says, what is the difference between a geosynchronous orbit and a geostationary orbit? In the textbook, it talks about this on page, I think, 300. And what I want you to know is what these two are. So a geosynchronous orbit is an object, a satellite that's orbiting around a larger mass that matches the rate of rotation of that larger mass. So let's use the Earth as an example. The Earth's rate of rotation, I'm not sure exactly what it is, but a satellite that is rotating around, or that's orbiting around the Earth at the same rate of rotation as the Earth, it will appear in the same location in the sky every 24 hours. So what would happen is it would kind of have a very predictable path. So predictable, in fact, that if you were to go outside and look at the same location in the sky, say at 8 a.m. every morning, you will see that satellite in that location at the same time. So it's important for a lot of artificial satellites, we want them to have this geosynchronous orbit. a geostationary orbit is an orbit that appears to be at the same point in the sky at all times. And this is because it is rotating around the Earth at directly above the equator. So let's look at the International Space Station. This question says that the International Space Station is at an altitude of about 350 kilometers above the Earth's surface. We have the Earth's mass, which is 5.98 times 10 to the 24, and the Earth's radius, which is 6.38 times 10 to the power of 6. We're asked to determine the speed needed by the International Space Station to maintain its orbit. So we have to find out what the v would be, and in this case, our r is not the radius of the Earth, because we're not going to the surface of the Earth. We're actually going a bit farther. So we have to add the radius of the Earth. We have to add that 350 kilometer altitude, to that. So our g, so this is again square root of g. So let's do bracket first, because we're going to do the square root after. G times the mass of our massive body, which is the Earth, to the power of 24, divided by our radius, and I'm going to add another bracket here because our radius is going to be 350 kilometers plus 6.38 times 10 to the power of 6. I'll close the second bracket, and then I will raise this to the power of 0.5 to get our square root. And we end up with a radius of, a velocity rather, of 7,700 meters per second. And you can write this as 7.7 times 10 to the 3, or I would accept it if you wrote 7700. We have two significant digits because that 350, we can't assume that that 0 in the kilometers is a significant digit. So we write that as just two significant digits. Actually, even if we had 3, it would still round to the same amount, but still it's important to know that distinction. Now, what I do want you to know when we do the homework for this, there is a, I think it's section 6.4 I'd like you to read as well, and answer some questions on that. This is this gets us a little bit into relativity, but this section kind of compares Einstein's theories of gravity and Newton's theories of gravity. So this is something you should know. There will be questions on this on the upcoming quiz, but it's also very important to understand because when we get into our Unit 5, we start to talk about the special theory of relativity. It's important to know these differences between different kind of perspectives on what gravity is. So I will leave it with that. Try the homework out. Again, if you have any questions, feel free to email me or add them to our class discussion board.